Hello, everybody. Thank you for coming. Today, I'm going to be presenting my master's thesis, Integration of a Custom 8-Degree Freedom Quadruped with ROS2. So, brief overview, in case this is your first time at a master's thesis defense. We're going to go over a bit of the background of this project, the kind of history around it, the objectives for this project. Then we're going to introduce our robot, including a hardware overview. Go over some mechanical improvements that we did, the software development that we did, and then some low-level testing that we ran. So we didn't get this thing to walk, but we did get it to do some pretty cool stuff that we're excited for. Then some conclusions and next steps. So a bit of background. This project really started off in 2020 with Bruce, which was the first iteration of the Cal Poly legged robotics group, attempting to make an 8-degree of freedom quadruped, and then move forward in 2024 with the planarizer, kind of expanding on controllability of the leg, and then also moving forward with some mechanical improvements. There were some problems with these designs, though there was a lot of successes. The frame and the leg had some rigidity issues, and then we were using a MATLAB-based controller. So getting locked into that MATLAB-based ecosystem kind of limits your operations, the possible things you can do. And then it also limits the frequency of the controllers that you can run. And then there was also some limiting sensing capabilities. So we can see Bruce here is kind of pretty bare bones in this first iteration. So our objectives are going to be to improve mechanical design, so handle those issues, and then as we integrate new hardware components, we're going to have to improve the hardware to be able to take on those. We're going to design a wireless mobile robotics development stack. So our development and our control, and we're going to be able to view the robot wirelessly. And that's going to give us some increased mobility because we were previously tied to the ground. And then we're going to maintain modularity in our hardware and software, and that's going to ensure that as we move forward with this project into the future, we can keep that long-term utility. So some of the things that we can make now are going to be useful into the future. So overview. This is Switch, so this is our upgraded version. We've got some new hardware here. And took a lot of work, but we got there. To highlight a few things, we're using the Steadywin Gym 8108 mini cheetah motors. We're going to talk more about these later. We've added an IMU, which is underneath the PCB. And then our compute module is the Jetson AGX OM Dev, which is very exciting. We get to use that. Additionally, we've got a LiPo battery in there. So we've got mobile power, and then also a power distribution board, or PDB, which takes that power and distributes it to motors. Starting out with the motors, these guys are more than just like your standard brushless motor. So they've got a brushless motor in there. They've got a 6-to-1 gearbox, and then they also have a microcontroller. And so we can connect to these motors via CAN protocol and send them a PD message control for positioning. So we can say, go to this position and maintain that position with a set amount of gain. This is pretty exciting, gives you a lot of different approaches for control. And then you can see the equation on the bottom there is describing how they're running that closed loop control. For our IMU, we're using a BNO08X. So this is a 9-axis IMU. It's actually got several different sensors on it. So an IMU is using an accelerometer, a gyroscope, and a magnetometer, and that's going to give us both orientation, velocity, and acceleration. Our communication protocol is either with I2C or SPI that we can connect to this thing. And this thing is operating at a maximum of 400 hertz, but plenty enough for us. And then just to touch on it a bit, this isn't the focus of the presentation, but we've got the NVIDIA Jetson Orin. The thing that sets these guys apart is really 3 reasons. They're quite low power, they're quite low mass, and the performance in AI is really something special while being both light and power efficient. So this is like, run AI on multiple video streams, like levels of power. We're not going to be using it today, but it really sets us up in the future to be able to explore new topics. So for our wired connections, we've got the motors connected over two CAN buses through CAN transceivers to the JetSim. And then on our I2C bus, we've got the accelerometer connected, the IMU connected. Both of the CAN buses are connected to the power distribution board. The power distribution board has two microcontrollers on board, so they can monitor the battery voltage and current and be able to send message over the CAN line to the JetSim, so we can monitor, the battery capacity and how much current's going through things. Okay, so some mechanical improvements. We started out this thing, the motors, when you tried to program them, you need to connect to a UART port, but the hip motors on the sides, the cutouts are a little bit too small, so you couldn't actually plug anything in while it was connected up. So you have to take the whole thing apart to program it and then put it back together. So we went ahead and widened those up, and we can be able to program them whenever we want to. Makes things a bit more convenient. The frame had that stiffness issue. It was actually, when we got it, it was held together by a strip of duct tape. When we're putting all this hardware on, we really need everything to be quite stiff, especially with the IMU. So we machined some frame stiffeners, installed that, and everything gets clamped together. So we got a big improvement in stiffness. For our legs, we reprinted them in glass fiber reinforced nylon, and that stiffened everything up, made everything a little bit more robust. And then we 3D printed some new mounting hardware. So we've got the battery mounting hardware for all of our electronics and BDD mounting, and then for our JetSim mount. And so this, stiffens the frame, stiffen the legs, and now we can integrate all of our new hardware. So now we can get into software development. So taking a step back, when we think about the main challenges for developing advanced robot applications, the three things that we're going to focus on are, first of all, writing the robotic software. Second, resource allocation. So now that we've written this software to run things like the IMU, the motors, we're going to be running all that in parallel. So we need some way to handle all of these parallel processes. And then we're generating a huge amount of data. We need to be able to communicate that data either on board the robot to get to the controllers where it needs to go, or to different programs that it needs to go, or in some cases, connect it to the internet and be able to access this thing anything in the world. So our solution for that is ROS2. So ROS2 is an open source project, and because of that, it's got some pre-built packages. So in some cases, we can just pull software right off the internet to handle some of the hardware that we're using. Then once we've got that software, ROS has several different ways to manage these processes. So everything is being run in a regular frequency. And then it's got ROS2 middleware, which is going to handle all of our communication. They usually use a DNS, but we're actually using slightly different middleware called Zeno. So just a brief overview of ROS so we get an idea of what's going on here. When we're writing an application, say we're trying to control a motor, we're going to write that with a program. And in the ROS world, we call that a node. We can make multiple nodes, and then those nodes can be running their own processes, but sometimes they might want to communicate. So say if we have a controller that's trying to control a motor, and we need to get a position from that motor. So the way that we would do that is through a topic subscription. So our controller could subscribe to the motor and get position data. And then our motor could subscribe to our controller and get a commanded position to move to. And that would kind of work nicely. What ended up happening in ROS2 is that the way that it was set up is you get jitter. So things wouldn't be completely consistent in the way that they were running. And so they wanted to make a system that was completely deterministic, where you knew exactly when everything was going to run, exactly when everything was going to hit. So that's why they made ROS2 control. So this is very similar to ROS, but it's like a sub environment, I'd call it. And so in the ROS2 control world, something that you would expect to be called a node is called a hardware interface. So our motor is going to be controlled through a hardware interface. And we're going to have one hardware interface per motor, right? And so now we want to control our motor. How are we going to do that? Well, we've got a controller interface, which is just like a node, except it's called a controller interface. And so this controller interface is going to take information from our hardware interface. It can run some kind of computation, and then it can send information to that hardware interface to control it. Where we did it using topics over here, now we're going to use state interfaces and command interfaces. And now this system is just a little bit quicker. ROS2 is written in C++ and Python, but when we move to the ROS2 control world, we're kept to C++ and C strictly. And so when we're doing this kind of stuff here, everything can run a little bit faster. But the nice thing, and something that we took advantage of, is even if you have something in the ROS2 control world, you can connect it to the generic ROS2 world through subscriptions as if they were nodes. So it can be really convenient like that. The good news, that was the most technical part. So this can fit into our whole stack here. When we were developing our stack, all the set of software that we're going to use to run this thing, we're going to divide it up into like our environment, our robotic framework, and then remote access. So we use VS Code, dev containers, and Docker to handle our environments. So one of the trickiest things when you're getting into these kind of complex systems and when you're working on a team is when you've got all these dependencies. If someone's working on a slightly different version or a slightly different configuration, you can be chasing bugs down for days and days. So this combination of VS Code, dev container, and Docker keeps a really strict control over your dependencies and your versions. And what we can actually do here is we're making a stripped down virtual machine. So a virtual computer that's running on your computer. This is really nice because if I can get code that runs on my computer and I'm running on Windows, with this system, I can send it over to somebody else running on Linux, and it will also work on their machine. Then we use ROS2, ROS2 control, and Zeno bundled together as our robotic framework. Zeno is handling our communication. And then for our high level visualization, we can use Foxglove. So we can have a model of our robot moving around as a digital twin. And also we can use No Machine to access the Jetson remotely. So we can get full admin access. All right. That was a lot of talking. Let's do something fun, right? So I was just talking about remote access. This right here is remote access into the Jetson. So this is the actual Jetson workspace. I go over here. We're going to see these messages changing here. So this is the CAN line. So this is telling us that the CAN line is sending messages. What we're seeing is the battery voltage being published by the PDB. Red is for one bus and then blue is for a different bus. This is VS Code. Over here, we can see we've got a dev container running ROS2. So everything is working here. And then what we can do, we can start up our Foxglove connection. And then we can start up our hardware. Now we're seeing a lot of messages coming through. So what's happening is all of our motors are publishing their position, their velocity, their effort simultaneously, and we can take that all into the ROS2 workspace. And now this is our Foxglove workspace here. And we can start up our zeroing procedure. And if we look at all the legs are moving. And now our robot is synced with our Foxglove interface. So over here, we have joint positions, joint efforts, and then here we have data from the IMU. So we have orientation, angular velocity, and acceleration. So if this is working correctly, I can move a leg here, and it matches up in our workspace. I will move around. If I pick up this robot, because we have the IMU, if you look at the top left side, we're going to see spikes in orientation and acceleration. And then we can get a readout over here. So we're seeing all the motors are zeroing and everything is working correctly. Do Control C, everything shuts down. And we just got a clean startup, ran our standard operating procedure, and then shut everything down. All right. Now on our implementation. So how exactly are we doing that? So we've got the Jetson on board the switch, and that Jetson is connected to a router in the back of the room. Through that wireless connection, we can manage our No Machine service and our ROS2 middleware service. In this case, me remoting into the Jetson, that was No Machine, and we could see ROS2 running there. But we actually have additional utility here. Because we're using ROS2, we can actually have other users connect to this Jetson and be able to access the ROS2 workspace, get all that information that Foxglove is getting without needing full admin access with No Machine. Looking at our motors, so just a kind of high level overview. The motors are going to get position control from position, velocity, KP, KB, and torque. That's what those motors need to operate. But we're running a state machine here with a couple of safety procedures. So we're going to add a couple command interfaces for flipping, state, and watchdog timer to make sure that our motors are all running correctly, and we can shut down quickly if we need to. When our motor interface is running, we get exposed position, velocity, and torque. So that's how we're able to reproduce that digital twin in Foxglove. Since we're getting position from the motors, we can forward that and make that model match up. And then our motors also send in CAN commands. So our motor interface is also sending CAN commands on hardware to motors. And all of that is bundled up into one motor interface. So in this case, when we're running on hardware, we've got 8 motor interfaces, one for each motor. Taking a kind of a different look, for our IMU, we got to do something kind of interesting. There was a really, really well-written ROS2 node for a BNO 8X, which is exactly the hardware that we're using. Several thousand lines long that handled all of the difficulties, but it wasn't in ROS2 control. So what we ended up doing is we can copy that node, and then we wrote an IMU forwarder. So all it has to do is subscribe to the topics that this node creates, and then forward it as state interfaces into the ROS2 control LAN. And then we've got all of the information wherever we need it. And then system dependencies. So we've got a lot of things going on here. And this is a diagram of all of the processes that we have running and what they're dependent on. So if we take a look at a motor, for example, For a motor to operate, we need to have power connected to it. Only if the power is connected is the CAN bus going to be operational. And for that CAN bus to operate, we're dependent on the CAN transceiver. And only if those two are working correctly can we worry about the hardware interface. So when we're trying to debug this thing, it's important to realize that failures are going to cascade upwards here. So if we have a low level like power failure, that's going to cause everything upstream dependent on that to fail. This kind of just helps us with debugging. And also, as we're designing the system, if some systems fail, it's going to cause everything upstream of it to fail. So to the best of our ability, we try to make this as thin as possible, but you're going to get dependencies. It's just kind of an inevitability, but we've done our best to limit those. All right, and now on to our low-level testing. We're going to look at reliability testing, our IMU benchmark, our IMU jitter test, and then an impulse test. So for our reliability testing, that procedure that I just showed you at the very beginning, we're going to start up our hardware, we're going to run our zeroing procedure, and we're going to shut down the system. What we're looking for is no critical error codes. We want everything to move into position. We're going to be dependent on that when we run the robot. And then when we shut everything down, we're looking for all the motors to deactivate cleanly. We don't want any error codes or anything like that. So our results, we ran 20 trials and we got 20 successes, which is pretty good. Something interesting though was as this thing starts up, motor 17 had a watchdog hit. And in this case, that's okay. As we're starting things up, things are going to take a little bit longer to run because you're starting all of that activation code. It isn't just like standard operating. But it does kind of beg an interesting question. Originally, the way that ROS2 control was organized, if you have any of these hardware interfaces take longer than you expect, everything in your system will kind of hang up longer. So what we ended up doing was doing a multi-threaded approach. And so that lessens our dependency on that. So one of our motors can completely crash and everything else can operate without getting hung up. So for our IMU benchmark, this is just to take a look at what an IMU is going to do, or IMU does in that standard operating procedure. So we're going to record some data with Foxglove, visualize it, and then we're going to rotate, and we're going to take a look at all of the readings from our sensors. So just like we saw in Foxglove, we're getting some nice output data over here. And then if we look at our orientation, it's a little bit difficult. We're expressing that in a normalized quaternion. So it's a little difficult to understand. But if you look at the linear acceleration, 9.8 meters per second squared, pretty close to 10. So as we're rotating this robot around, we see X is positive, and then we rotate 90 degrees, and we get Y being positive, and we rotate again, we get a negative X, and we rotate, and we get a positive Z. So we're seeing what we're expecting here. And then additionally, we can focus on the magnetic field here. So the magnetic field is helping us with orientation data. And then we had an interesting question about that. Since the magnetometer is going to be recording electromagnetic fields, we've got a lot of motors here that are inducing electromagnetic fields. And not only that, they're FOC motors. So they actually have a magnet on the shaft, which is acting as an encoder. So this is another rotating field just as the motor rotates. So the question is operating the motors on this thing going to make the IMU go haywire? So what we're going to do is we're going to do a jitter test. We're going to shake all of the legs. So we've got an EMF being induced. And then we're going to look at the standard deviation of IMU readings to make sure that everything's operating as we expect. And when we do that, you can see this red line is when we kick everything off. Everything is looking really nice. If we look at our standard deviation before and after, these are very small numbers, which is what we want. We want our standard deviation to be very small here. Our magnetometer here is the thing that we're most concerned about. And we can see a very, very slight increase here. And if we check our orientation, which is what we're going to be extrapolating that information out of, we can see the change in our orientation as our robot should be staying still. There shouldn't be any change here. But it's increasing, but very, very slightly. So in this case, this is really good news. This is telling us that operating our motors isn't going to cause our IMU to give us false readings. All right, and then impulse testing. So we got this robot standing up, and we can do that because we can just send a position command to all these motors to say, hold this position. And then as it's standing, we can apply an impulse, we can hit it, and we can read everything in Foxglove and just make sure that everything is operating as we'd expect, and also that this thing recovers from the impulse. This was a fun one. That last bit was me telling Jack that I had to kick it next, like Boston Dynamics. So our impulse testing, everything matched up pretty nice. We can get a nice twin between the two of them, as we saw earlier in the demo. And then as we look at our position and our effort from our motors, we can see right as our impulse arrives, the effort of the motors increases as it's pushing to move back to the normal standing position. And we can see the position of the motors recover back to that initial position. In addition, if we look at the IMU, we can see the same thing happening. Our orientation of the body of the robot changes slightly, but then we can return right back to that steady state. So conclusions, we were able to improve our design here, and we're able to integrate all of that new hardware we're very happy about. We were able to specify a mobile robotic development stack, and we achieved that increased mobility. And then we also maintain modularity in our hardware, which is going to give us utility in the future for the system. So as we move forward to a 12-degree freedom robot, or in the future, we can use the software that we were using. There's our next steps. So looking at this system, we had a bit of a hiccup in the middle of it with the PDB. It was quite a challenging piece of hardware to actually put together. So that's really the next step for this guy to be able to get up and rocking. Once we do that, which I expect will happen very soon, this system is really set up for reinforcement learning. It's got the hardware for it. The stack that we made is really primed for that kind of support. So probably reinforcement learning for walking. And then Kai's working on the 12-degree freedom system, so he can reuse some of the software that I wrote, and also learn some of the things that we learned from this hardware integration. And then something interesting, the way that we set up this project makes new applications of this system very straightforward, I'll say. The theory is that with two configuration files, you can set up the same level of controllability that we had on this system with a different system. So if you have, say, a 12-degree freedom robot using same IMU and the same motors, all you have to do is add a couple descriptions of your motors, just tell them what their commands are, what their buses are, and you get basically the same controllability. You can go in and access them in the same way. All right, and then as a final, just thank you to my board members for coming, and then also everyone who's helped me get here. I'm very appreciative, and I'll open it up for questions. Yeah.
In your IMU jitter test, where the motor is trying to hold position?
No, so they had two positions that they were oscillating between the two. So it was some very small movement. The challenge with that test was inducing a field without inducing like a mechanical movement, because I wanted the machine to stay completely stationary. So any change, so any change would just be coming from those fields.
a general question, like, do the motors have the torque durability option or
Yeah.
the position or both? Like,
Both.
can you switch between them?
Yeah, it's kind of interesting. The motors are running proportional derivative control. And so you send them a proportional gain, a derivative gain, and then you can send them a position and a velocity, and they will run PD control with that data. But they also have a torque feed forward command. And so you can choose, I can run like position control, but then also add in a torque command. Or I could just set KP and KD to 0 and then run entirely off of effort commands.
It's purely torque control.
Yeah, purely torque control. So if you just set KP and KD to 0, then when you're sending effort, it would just behave exactly like a torque control command. That's actually the way that we were planning on controlling it.
I've always been a little bit scared of ROS. You make it seem very approachable in your presentation.
Yeah.
For someone who's versed in this sort of realm, but not ROS, what kind of startup cost is there to get this working?
That's a really, really good question. I would say that ROS, like ROS2, is very new. You look online to see what robots are using ROS2, you're not going to find a whole lot. And that's because the documentation is pretty scarce. It's getting a lot better, but I wrote it in the paper, and me and Jack have talked about it before. When you're trying to solve a problem in ROS, it's going to take you like 3 days to a week, whether it might have taken you an hour if you were using like standard US code. So if you want to do something like having like a distributed network of robots that are connected to the internet, and you can get simultaneous video streams and you can run really advanced control, ROS is probably a really good option for you. But if you're trying to do something pretty basic, like a Romy project, something where you're really limited on time, ROS is probably not your best option, just because of the amount of time that it's going to take. Like, now that we've kind of had the experience with ROS, I feel pretty good about, if you ask me to make a hardware interface, I could get it to you. But just as a general rule, everything's going to just take a bit longer.
So as a follow-up, do you have any sort of onboarding process for future grad students? Do you have a user manual or something to go with what you and Jack put together?
Yeah, so the plan was to make a user manual. I think that's still what we're expecting to do. Even with that, the trials and tribulations of ROS, there's so many like subtle things that you need to worry about. So as I've been making this, whenever I want to do something, I'll set things up in shell scripts, and kind of including that, that container and everything. That should take a lot of the grunt, like some of the worst parts away from just like that startup procedure. These shell scripts are just like a couple like very specific commands, and it's just like one of those cases where you'd expect something to be really clear online, but it's not. And so hopefully with these few scripts we can.
And then you'll be on call for the lifetime of this.
Oh yeah, for sure.
Yeah,
honestly, I think one of like the best things that we can do for this club is like we have a very open communication with Kai and Alan, and so as they're working through this, that they know that they can call me up and why does a hardware interface work in this way? Like you can save like weeks worth of time with one phone call. Like it happened with us when Minimum came on board.
Great.
Setting up a test for dynamic loops. That's a good question. So starting out, I'm going to expect that we're going to be looking at walking. For that, we really want everything to be as simple as possible. And so we kind of talked this out. If we use like a a PVC setup. I've seen it in like some other approaches. You just have a frame, a PVC, and you have it rigged together with some rope and you attach it to the robot. And you just make sure that rope is just a little bit shorter than what it hits the ground. As you're running all of this testing, as this system is going to fall over, it just stops you just short, right? And so that's going to save the hardware. Moving forward, doing more of the high speed kind of approaches, we can look at the treadmill. That's when the treadmill would really, you can really take advantage of it, because once you get up to like a certain speed, it's worth putting in the trouble to make that whole system work. But as long as you're doing something pretty slow, just a really bare bones frame should be enough. Yeah. Yeah, that's a really good question. So we actually did have the case where the PDB burned up one legs section of the power distribution. In that case, it was operating within what we'd expect for current. So that seems to be a known design fault with the PDB and not going to cause that PDB to fail. I believe we have that issue handled now. And so moving forward, I believe the next generation of PDB shouldn't have that problem. The motors have torque limits built in. The motor hardware interfaces also have safety limits for torque built in, and we tested those. So in the case that it does pull more than expected current, the motor just goes slack, just so that we don't run out any of the electronics. So I think that as long as the PDB is built within spec, that shouldn't be an issue. But of course, there's some, MIT documented kind of how difficult that is, trying to put a fuse on the system. If you try to make the MIT Manichi to do a backflip, they can't tell the difference between a backflip and like an overcurrent event. And so they just have to completely disconnect the fuses for a second when they do a backflip. So it is a bit of an issue, but I think as long as the PDB gets built within spec, it should be okay. I think it would reduce the total weight, but I don't think that's really the primary concern. No matter what, if you're going to do something like, I believe doing like an incredibly dynamic gate is going to give you a higher current spike than just the weight of the robot. Sure, if you lower the weight of the robot, that would be, you have more wiggle room there. But yeah, I think it's mostly just making sure that the electronics hardware is built sturdy enough. And as long as we're avoiding backflips, then you can use fuses. Yeah.
I think like after the
yeah, that's a really good question. The really good news is that as long as you're using the same hardware, you can control it in a similar way. So the motor hardware interfaces that I wrote will work on that motor, like no matter what. So we could, let's like say we're going to make a bipedal robot with two legs. Dramatically different chassis. We could even use a Jetson Nano, completely different computer, but we could be using the same IMU and the same motors. In that case, in our configuration file for this machine, we would describe those motors. And so we'd say, we've got this motor on this bus with this address. and this motor on this bus with this address. And then we would introduce the robot description file called a URDF. And technically those are like the only two things that you need. So if we put those in and we could get the kind of controllability of the robot, like the motors, so we could tell the motors to move in exactly the same way. And we could get IMU data out in exactly the same way. We could also probably reuse the Foxscope interface without thinking anything. But like you might have to rewrite the program for zeroing procedure, for example, because just the hardware design of that robot might be slightly different than the hardware design of this robot. But the hardware interface for the motors and the IMU should still stay the same, and that should save you a lot of time.
Video of the internal discussion. And then we also will have like our audience that will be outside.
Yep.